Great. So yeah, great to have a chance to present to you all again. So today I am talking about a model of scientific communication, which is a paper I worked on a couple of years ago with Jesse Shapiro at Harvard. So the sort of point of departure for this project is a classical model of statistics and decision theory dating back to Walt. Right, we're basically in a framework that's come up in a number of the talks over the course of this conference. We're going to think about an analyst who observes data X from a space of possible data realization script X. And they're going to use those data to form an estimate of an unknown parameter, say theta. Now, we usually think of the estimate of theta being good if it's close to the true value of that parameter, right? Which we'll formalize by imagining estimation as a decision problem. Right, where the estimate is a decision, say D from a set of possible decisions, script D, and we're picking that decision to try to minimize a loss, right, where the loss depends on the decision taken and the true parameter value. Right now, this sort of framework, right, where we think of choosing an estimate to try to get as close as possible to the truth, is the dominant paradigm for point estimation, right, where, for example, we might take the loss to just be the square difference between D and theta, giving us sort of canonical squared error loss, very standard loss to think about for estimation, but also for many, many, many other decision problems, right? And this decision-theoretic framework is the foundation for most optimality claims, right? When we say that something is optimal, we usually mean that it's optimal sort of under this decision-theoretic setup. Now, if I were to sort of take that verbal model, put it in a picture, right? The basic model we have in mind is that there's a data generating process out there in the world that gives rise to data. Those data go to an analyst. The analyst uses those data to form an estimate or decision, and that estimate or decision, together with the underlying state of the world, determine the loss. And I would argue that this basic setup is very descriptively realistic of sort of how we think the world works for certain types of settings. Think, for example, of an analyst who works at a firm. Am I signing in on another device? Should I allow you?
No, it's not.
Oh, okay. I'd rather not change my password. Okay, thank you. Right, so I think this basic model, this sort of traditional model, is sort of a good description for certain types of settings. Think, for example, of an analyst who's working at a firm that has to make a pricing decision. At the end of the day, right, the price set by the analyst is what's going to determine the loss or profit or utility of the firm. Right, and so this sort of description, where there's just a decision that feeds directly into the loss, seems like a pretty good one. In this project, though, we're going to be thinking about another type of setting, where we've got a data generating process that gives rise to data that goes to an analyst. The analyst then uses those data to form some sort of a report or a summary of the data. That report is then observed by an audience, where members of that audience, based on the information in that report, then compute their own estimates or their own decisions. And it's those decisions made by the audience that ultimately determine the loss.
So you're assuming, I guess, there's no agency issues, right? So the analyst is just kind of selfless. And
yes, exactly. Right. So yeah, exactly. So I'll sort of get to this a little more when I sort of describe the formal model setup. But here, what we're going to do is sort of take, in some sense, a very optimistic view, where what the analyst is trying to do is just to serve the sort of interests of the audience. And the main point of this project is just that even if I say there's no agency issue, there's no misaligned incentives, simply having these be different agents, right, and having the audience be heterogeneous actually means that this is a different model than this one, right? And so you could also, of course, think about layering on agency problems, layering on communication problems, whatever. That's, of course, going to introduce even more of a wedge. But basically, the point we're trying to get at here is just that what seems like sort of the minimal step you could take towards having, a distinction between the analyst and the audience is enough to make a difference here. And again, I'll be more precise about that when I get there. Now, this alternative model that I'm going to work with, we would argue, seems like a more realistic description for certain types of scientific settings. Think, for example, of an analyst who's reporting to scientists with diverse opinions or policymakers with diverse objectives. Right? If I'm sort of a data analyst calculating some stuff that's then being reported out to a bunch of different policymakers, what matters for social welfare isn't really the number I report, right? What matters for social welfare is what the policymakers do with that information, right? And that's sort of what we're trying to capture in this model. Yep.
would time be one specific example of that? So kind of, if I think of an optimal decision here and now, that may be different from the information that is still valuable once I've gathered more information over time.
Yes, exactly. And I'll point to sort of how you can embed that in this framework when I get there. But yes, exactly. Sort of one version of the audience could even just be sort of, I'm calculating something and then reporting that to a future version of myself or to someone else in the future. And basically, they're going to be basing their decision just on the report, not on the full data. Again, I'll get there.
But there is something that prevents you from just making the report equal to the data.
I'll get there. So, as I sort of already sketched, today, the basic point is going to be to argue that these two models represent fundamentally different and at times conflicting views of the analyst goal. And in particular, that even though we sort of haven't put in agency problems, we don't have a conflict of interest, these models can still lead to very different recommended procedures. And then I'll wrap up by discussing the implications of that difference for empirical research. So with that, getting to some of the questions that have been anticipating this, let me tell you a little more formally sort of what the timing is in the model that I'm thinking about. So we're going to have an analyst who's going to publicly commit to a rule, where a rule is just a mapping from data realizations to the set script D, right? The set of possible actions, the set of possible reports. The analyst, after committing to a rule, is then going to observe data X, right? Where X is drawn from a distribution governed by the unknown parameter theta. The analyst is then just going to apply the rule to the observed data and so report C of X to an audience, right? We'll denote that audience by script A. That audience is going to consist of a collection of agents, where each agent in that audience is then going to select a decision after observing the report, will select a decision D and realize a loss L that depends on the decision they made and on the true parameter theta, but does not directly depend on the report. Right, so if I'm reporting estimates to policymakers, what matters for their utility or social welfare is the decision they make and the state of the world, not directly the number that I happen to report. Now, I've sort of introduced this audience of agents script A. Agents in that audience are going to differ in their priors on theta. Right, so I'm going to write expectation subscripted by A to denote the expectation taken under agent A's prior. Now, all the heterogeneity in the agents is going to live in their prior, right? Agents are sort of going to have the same loss function, just heterogeneous priors. So I can basically just identify agents with their prior and write the audience just as a subset of the set of beliefs on theta, right? So basically in this model, an agent is just a prior, right? So as I said, this says that all disagreement is expressed via priors, but I should note that this actually is less restrictive than it might look like. Basically, if you give me a model where agents have heterogeneous losses or even heterogeneous likelihoods, right? My view of how the data are distributed given theta is different than yours. I can basically rewrite the parameter to re-express that as a model with just heterogeneity in the prior, right? So in some sense, the other sorts of heterogeneity you might worry about can be embedded in this. Yes?
I'm just surprised it was, well, it seems more complicated, which is to use different distributions for each A, was you use that rather than giving the different loss functions, which seemed like a rather simple. There must be, I'm just wondering why.
Yeah, I mean, right, in some sense, you can go, like we show in the paper, you can go back and like they're equivalent representations actually. So sort of, I can take a model with heterogeneous priors and rewrite it as one with homogeneous priors and heterogeneous loss. And if you give me a model with heterogeneous loss, I can write it with homogeneous loss and heterogeneous prior. So in that sense, it's purely a choice of sort of how to write it down. This makes it simple because I'm just working with a set of distribution, right? Basically, the audience is indexed by a set of distributions, which is a little simpler, at least for me to work with, than it being indexed by a set of loss functions, but it doesn't matter. You can represent it either way. Coming to Jan's question, right? One version of this that you could think about is that, right, maybe actually, right, it's not that there's multiple agents in the audience, there's just a single person in the audience, but I don't know what their belief is. Right, in that case, script A is the set of beliefs the set of priors they could have. Right, and so then in some sense, rather than thinking about trade-offs across different people in the audience, I'm thinking about trade-offs over different beliefs that the audience could have where I don't know which is the right one. Yep.
Can you just remind me though on this equivalence? So one direction is obviously where you just rewrite the loss function by the relative prior, whatever the relative prior. Or do you go the other direction?
Yeah, so basically just add an additional parameter, right? So I haven't said the parameter is finite dimensional or anything. right? So basically add an additional parameter, right, to the parameter vector that just indexes the loss function.
Okay.
Right, and then basically just give people a dogmatic prior on that
Got it.
parameter.
And it seems like the analyst's prior has no role to play because.
Yeah.
Right.
The analyst here isn't even going to have a prior. Exactly, right? I mean, part of the reason we're going to set it up this way is exactly because, right, so you could think about having the analyst have a prior, right, which would raise questions of, well, if the analyst has a prior and the agents have a prior, does the analyst think the agents are wrong, right? Or does the analyst think the agents have observed additional information, and how do you want to handle that? Here, we're sort of just going to take an agnostic view of the analyst has no view of what the right state of the world is. They're simply trying to give the audience information that the audience thinks is useful. And again, I'll be a little more precise about exactly how we're setting that up here. Right, so specifically, what the analyst is going to try to do is to minimize the expected loss, right? Or to introduce a word I'm going to use for that for the rest of the talk, standard terminology in this area, the risk for the agents. Right, and something we've already touched on here is that here we're modeling the analyst as benevolent, right? Basically, the analyst is not trying to trick the agents, is not trying to convince the agents to do something. The analyst is purely trying to help the agents achieve their own objectives. And so in that sense, you could think of we're modeling the analyst here as sort of very, very benevolent. Right, and obviously, if you make the analyst less benevolent, that'll introduce further wedges between sort of the analyst and the agent. But here we're taking the simplest benevolent case. In this setting, we're going to think about two possible definitions of risk or expected loss of a rule C for an agent A. The first, which we'll call decision risk, corresponds to the classical model. Right, and this is basically the expected loss when I plug the analyst choice C of X into the loss function. Right, so this is basically the expected loss as if the under agent A's prior, if the analyst were making the decision on the agent's behalf. By contrast, communication risk, which will correspond to the alternative model I set up at the beginning, is this object. Right, so basically, to spell this out a little bit, right, what's going to happen is the analyst reports C of X. After observing the report, the agent is going to form their posterior belief on the parameter theta. Right, they're then going to choose the action that minimizes expected loss under that posterior belief. And the communication risk is the ex ante expectation of that whole object.
So C of X and D have the same type, they're both like that.
Yeah, so that's sort of a modeling choice we're making here is basically we're choosing C of X to look like D. I'll talk about sort of where is sort of that restriction is basically one bit of work that restriction is doing is it's letting us write, basically write this thing, right? As if we're just plugging things into the loss function. For communication risk, I could report something that doesn't plug into the loss function. That's sort of a bigger dimension than the action that will ultimately be taken. For our purposes, having these things sort of be the same is going to be convenient. But in some sense, if you allow C of X to be bigger, it's just going to put more of a wedge between these two things.
But a lot hinges on the fact that you can't let CX equal X. Right?
Again, sort of, I'm going to talk about that, right? I mean, basically, what I would say is absolutely, right? In some sense, just, right, I'm going to talk about it. But basically, the point is, if I could just let C of X equal X, right? There's no communication constraint. Then in an ideal world, I would just want to report the full data to the audience, let them do their own thing. That's exactly right. Now, what I would argue, sort of the point I'm going to make in the rest of this talk is that if I constrain the class of rules, right, if I think about the choice between, say, rule A and rule B, these criteria can recommend very different choices. Now, I totally agree that in principle, the recommendation under communication risk becomes very simple if I say I just want to report the full data. However, I would also say, as a description of what we're trying to do in scientific communication, I think that runs into some problems. Right? For example, why would anyone ever write a paper about publicly available data? Right? In principle, those data are available. My paper is my empirical analysis is adding no information over and above what you could get for downloading them for yourself. Right? And so in that sense, basically, my view is there are some communication or data processing constraints in the background here. We don't totally know how to model them. And so for this talk, I'm going to think about these two criteria over particular comparisons of rules I could choose. But totally agree, you sort of could think about, if you thought about this problem with no constraints, you would just want to report everything.
I guess an alternative view would be that I, as the expert, have some prior how to turn something very complex into some abstractions. And then once these abstractions are there, you have a good prior for to work with them. Is there some mapping to that view that we're kind of combining expertise? I understand that may not be the same. I wonder whether there's a connection.
Again, if the thing is, if there's no communication constraint at all, right, then why I want the expert to basically just report the data appended with their full prior.
Yeah.
Right. And so that's the right. I think my view is sort of thinking about what people actually do. It feels like there is some constraint. I'm like, I don't know how to model it.
Good.
Right. And so basically, but in some sense, the point that like what the right, but I would argue that basically what the right constraint is separable from the question of is decision making and communication the same objective? Right. My hope here is just to convince you that they are a different objective, and then we can think about the question of what the constraints are.
Right, completely with you on that.
Yeah.
So I think it would be interesting to think about the nature of these constraints harder, right? And I've been trying to look a little bit into like what psychologists and others would say on that. It's all ends up being fairly ad hoc in terms of like limited attention.
We spent quite a bit of I would say we not having a good answer on this. I mean, one can always think about things harder and better, but our not having a good model for the constraints, I would say, is not a function of our not having tried. Like basically, exactly as you're saying, we sort of we tried sort of some things coming from psychology. We tried like some information theory type constraints, and like all of them ended up producing something that either felt kind of ad hoc or did not feel like it actually mapped to just thinking realistically about, oh, would rule A or rule B be something I could report? So basically, I completely agree. I think the question of what a realistic constraint is super duper duper important. Basically, we tried to think about it, did not end up getting traction. And so for the purposes of this project, basically essentially for the purposes of this project, it turns out we can think about this distinction while punting on that. But I agree that like long-term, that is a very important and very interesting question.
You take the COVID vaccine trials, which keep coming to my mind as a canonical example here.
Yeah.
I mean, in some sense, the data was very simple. It just like it really was a list of some thousand people, and yes, no, maybe one or two characteristics, and yet they were still advised to compress it and give a soundbite, even in the which suggests the constraints that you were just been talking about are really binding.
Yeah, no, exactly. I mean, so that absolutely. I mean, one thing, right? I guess one thing I want to flag here is that in this case, again, like a sort of an assumption we are making, which gives us traction in the model here, but which is sort of descriptively almost certainly not quite right, is basically we are assuming. I'm going to say I can't communicate the full data. I'm just going to think about communicating these limited things. But once I communicate that, I'm assuming that agents sort of fully optimize, right? That basically agents can apply Bayes' rule, form their posteriors, choose the optimal action, et cetera. Another motivation for choosing simple rules is basically simple communication rules is I think people are going to mess up, And so in the example of the COVID trials, in some sense, there's a question of, if I just I could report, right? If it's like a relatively simple set of covariates, I could just report the grid of success probabilities and the grid of like how many people were in each cell. And so is the reason I don't want to report that I think people aren't going to know how to interpret it, which is plausible, that it's sort of too much information to communicate, or that I think people are sort of going to get confused by it and make a mistake. And some of those are nested in the framework we're using here. The get confused by it and make a mistake isn't. But again, as a feature of the world, seems pretty plausible. Does that make sense? Yeah. So I just want to flag that there's some versions of that case which we're sort of assuming away, but other versions of it I do think fall into this. Great. Yes.
So I don't know if this is the way I would approach scientific communication in the sense I would understand that science people would like to report something close to the truth. However, here it feels like they actually have incentives to report something very far from the truth if they believe that the agents have completely misguided prior.
So that's not here, right? So here the analyst is not trying to persuade the agent to take any action. Right, the analyst is simply trying to give the agents information that the agents think will be helpful. Right, so what you described is sort of a paternalistic motive, right? Basically, I think the agent has a dumb prior, so I'm going to give them data that's sort of over here to pull their belief back to where it should be. That sort of is an interesting model, but it is not something that's here, right? Because that would sort of be the analyst has a prior, they're trying to convince the agent to take a good action. Whereas here, I'm just saying the analyst doesn't even have a prior, right? I know the audience has a prior and the analyst is just trying to give the audience information the audience thinks will be useful. So let me actually go to let's think through what these losses are in the case of squared error loss, and this may clarify things a little bit. So if we think about squared error loss, right? So L of d theta is just the squared difference between d and theta. Decision risk is just mean squared error, right? So the decision risk of C under agent A's prior is just the mean squared error of C under that prior. By contrast, communication risk, right? If you sort of work out what it is the expected posterior variance. So this is for agent A, if they know ex ante that the thing that's going to be reported is C of X, what do they expect their posterior variance is going to be after observing C? Now, Tanika's question, right? Obviously, for this one, I need C and theta to be the same dimension. For this one, I don't, right? So for this one, I could let C be something much, much bigger than theta. But if I do that, that's actually just going to make these problems further apart. And so in that sense, the case where I'm constraining them to be of the same dimension is in some sense forcing them closer than these problems would be if I did the unconstrained version here. But I agree that sort of is a constraint of putting on the problem. Now, one thing I want to highlight up front is that because we're assuming the analyst is benevolent, this communication and decision distinction is irrelevant when there's just a single agent in the audience, right? Basically, if the audience just consists of a single prior, then what a benevolent analyst should do is just to pick the report equal to the optimal action for that agent, right? In the case of squared error loss, the posterior mean, and then the posterior mean is optimal for both of these problems, right? So basically, if there's just one person in the audience and I know what their prior is, I just solve their decision problem and tell them what to do. And since I'm benevolent, that's great.
Can I ask a technical question?
Yep.
So I guess here basically you're restricting X to C to be a real number, right? But then, I mean, in principle, I can almost can code anything with a real number.
Yeah. No, exactly. Yep. And so that's why, as I said, we're going to be thinking about limited classes of rules. So for example, rule A versus rule B, right? Because otherwise you can do goofy things like I can encode an infinite amount of information in a real number by just putting in the decimal expansion or something silly like that. Yes, absolutely. So again, I would say this comes back to the point of we don't know what the right? I would sort of say as a description of what actually people can communicate in scientific practice, saying I'm going to take the US Census and I'm going to encode it in like one real value point estimate seems like a goofy description, right? So I'm going to say that's not what we actually can do. But right, basically, because I don't have a good description of what the feasible set is, we're going to compare particular pairs of rules.
Like another way of saying that it's not just a feasible set of reports, but a feasible set of rules.
No, but right, exactly. No. Yeah, but we're going to constrain the feasible set of rules. Yeah, that's right. Yeah, exactly. So to make all this a little more concrete, let me give you an example. So imagine an analyst who conducts a randomized trial with a binary outcome. And imagine the analyst's goal is to learn the vector of success probabilities, theta j, at each of a finite set of ordered treatments, 1 to j. For instance, this could be the probability of purchase at a set of prices, right? So I've got a set of consumers and I'm thinking about offering them a product at prices, P1 up to PJ. And I want to learn what's the probability they buy the product at price 1 up to what's the probability they buy the product at price j. Or alternatively, right, this could be more of a labor economics example, probability of callback at a set of unemployment spell lengths, right? So basically, I'm thinking of people who have been unemployed for 1 week up to j weeks. And I want to know what's the probability that a randomly selected employer is going to call this person back if they've been unemployed at week 1, week 2, up to week j. Now, suppose, for the sake of this example, that we know ex ante that these success probabilities are decreasing. Right, so theta 1 is greater than or equal to theta 2 up to theta j. Right, in the demand example, this would say demand slopes down. Right, so the higher I make the price, the fewer people weekly buy it. Alternatively, right, in the unemployment example, this would say that the longer someone has been unemployed, right, the fewer employers or the less likely employers are to give them a callback. Again, right, neither of these has to be the case as sort of a law of nature, but for the sake of the example, suppose we all agree that these are true. And again, we're going to think about quadratic loss, right? So my goal is to minimize the squared, the ultimate goal is to minimize the distance between the decision D and the true parameter value theta, right? I want an estimate that's close to the truth at the end of the day. Now, suppose that I have n independent observations for each treatment. And let's let x1 up to xj just denote the fraction of successes that I observed in my experiment over these j treatments. Let's take the decision space D to just be the sample space script X, right? So basically, this is a case where the sample space, the decision space is rich enough that I could just report the full data, right? That is an option I have in this case. And let's let the audience script A consist of all possible priors, subject to this restriction that the thetas are decreasing in J, right? So basically, this says that everyone agrees that the thetas are weakly decreasing, but priors can be heterogeneous about everything else. Coming to Max's point, right, we're going to consider a restricted set of rules here to start. So let's first think about the full data rule, right? So the full data rule just says I'm going to report a j-dimensional vector where the jth element of my report just corresponds to the jth success probability, right? So this is just estimating this vector of parameters theta by the vector of results in the experiment. Alternatively, we could also think about a rearranged data rule, which I'll denote by C star. Here, the jth element of my report is going to correspond to the jth highest element of x1 to xj. Right? So what I'm going to do here is I'm going to run my experiment, then I'm going to take the experimental results and sort them in decreasing order. And instead of reporting the raw experimental results, I'll report this sorted list without telling you which probability originally correspond to which j. So just to visualize it, right? Imagine that j is 12. I run the version of this experiment where these are callback rates, and these are the success probabilities I get. Right? So among people who say they've been, among CVs that say they've been unemployed for 1 week, the callback rate is whatever, 19%, mostly decreasing as I go up to 12 weeks. Now, the full data rule would just report this data, would basically just report this out. By contrast, right, the rearranged data rule would observe that, right, this is non-monotonic in 2 places. So I'm going to instead take this sorted in decreasing order and report this sorted list. Now, if I say that my goal is to, as an analyst, is to report something to you that's as close as possible to the truth, there's a sense in which this looks like kind of a goofy report. Right? In particular, we all agree, ex ante, that the success probabilities are decreasing. But this thing is non-decreasing, so we know that this can't possibly be the truth. And yeah.
Just as a standard decision problem, the rearranging is a good idea, but it's not just projecting onto the flat.
No, yeah, you can, I mean, right, I guess what you can show that rearranging in this way leads to a rule, this rule dominates this one in decision risk.
But like just the projection on the monotonic functions would presumably be better, right?
I don't know which of those is better, actually. I'm not sure one or the other. Right, I guess one thing I would say is the non-parametric version of this was proposed by Chernijoukov et al. 2009 in a Biometrica paper. So if it's super obvious projection is better, that was a weird publication decision. Right, so, but yeah, I guess in terms of projection, I'm not sure. But certainly what you can show, right, is basically rearranging the data in this way guarantees a weakly lower risk under all priors and a strictly lower risk under some prior, right? Basically, you can show that under squared error loss, doing this is guaranteed to get you closer to the true parameter value. How doing this compares to projection, I'm not exactly sure, but actually the negative argument I'm about to give would also apply to projection. So if you prefer to think about it with projection, you can also do that.
I mean, the information loss is there either way.
Yeah, exactly. So in that sense, either one.
Yeah, so are you about to explain why? Or
why this improves it?
yes.
No, but I can give you an intuition, right?
Because I just can't, at the moment I can't see why anyone could rearrange those dots to be in decreasing order. So each of the recipients of the data could do that themselves.
Well, but that's right. So I agree with you. But again, right, that depends what the goal is, right? If I say my goal is to report an estimate that minimizes squared error loss, right? Then basically, if I can show you that rearranging in this way, right, I can show you basically that rearranging in this way under the monotonicity restriction decreases the loss of data realization by data realization, right? And so basically I say my goal is to report something to you that's as close as possible to the truth in this sense. I should always rearrange.
Yeah.
Oh. Okay. Okay. Right, basically, but exactly to your point, if I'm instead saying that people in the audience are going to make their own decisions, then this is a goofy thing to do. Right, it seems like you already have that intuition, but let me briefly sort of sketch it out. Right, so in particular, the sort of rearrangement rule maps this data realization to this sorted list. On the other hand, it maps this data realization to the same list, and that data realization to the same list. Right, but if I think about these three different data realizations, at least for me, I would come away with a very different posterior belief about how steeply sloped the relationship is. Right, even if I am certain ex ante that it's weakly decreasing, right? If I observe this data realization, I think it's probably a pretty shallow relationship. Whereas if I observe that one, I think it's pretty strong. And if all that I'm given is the sorted list, I don't know which of these occurred, right? And I'm unable to back that out from the reported data, right? And so that basically immediately from that, you can see that reporting the full data dominates reporting the rearranged data in communication risk. Right, basically rearranging the data throws away decision relevant information. Right, and to your point, Max, if I instead projected on the set of monotone functions, I would get the same property.
I mean, I know it's a distraction, nonetheless. But if you think of just estimating one mean of one normal draw, right? Like rearranging corresponds to mirroring it. Say if it's positive, I just flip the sign as opposed to setting it equal to 0, which seems like a very weird.
No, I mean, again, in some sense, right? My point is, this, you know, rearrangement. Yeah, exactly. Rearrangement was recommended as an approach for cases where you have shape restrictions. So if you, and basically our negative argument for rearrangement applies equally well to your preferred solution. So basically, that's fine. Does that sort of, I think this is the intuition you're having? Yes, perfect. Other questions here? Great. So far, we've shown that different models make selection from a given pair of rules, C and C star, right? So I basically gave you C and C star, and I said, oh, C dominates C star if we use decision risk, C star dominates C if I use communication risk. In this example, a stronger statement is in fact true. So we're going to say that a rule is admissible in a given notion of risk if it is not dominated by any other rule, right? So there's no other rule that's better for every prior. In this example, you can actually show that any rule that is admissible in decision risk is inadmissible in communication risk and vice versa, right? Basically, there exists no choice of rule that dominates, that sort of resolves this choice of risk, right? So in this example, the conflict I'm getting between C and C star is not about sort of something funny that I'm choosing these particular rules. Like that basically has to happen for any admissible rules. Now, coming back to the discussion we had a bit earlier, in this example, the reason you can show this is because of the discreteness of the sample space and the discreteness of the communication space, right? Basically, because the the data here only take a finite set of possible realizations, right? And basically that ends up giving you sort of a discreteness to the signal space that allows you to get this inadmissibility. Otherwise, to your example earlier, Max, right? If I said the sort of set of decisions I can take here is continuous, right? I could sort of do the decision optimal thing and then bury a description of the full data arbitrarily far out of decimal expansion and like play kind of silly games like that. Right, the discreteness of the
uncountably infinite would give you that, right?
Yeah, exactly. But again, you know, like as a description of sort of what people are going to do in practice, I do the decision optimal thing and then bury the data set arbitrarily far out in the, you know.
That's obviously silly, but it is a substantially different thing to restrict the report space or the reporting function space.
Yeah. Oh yeah. No. Exactly. Right. And so right here, and so I agree with that. But in some sense, for our right, I guess what I would say is I think the true constraint right? If I think about communication in practice, I think the actual constraint is on the set of reporting functions in some sense. I don't know how to model that constraint. And so again, here, my focus is just on saying these are different criteria. And for that, it suffices for me to exhibit cases where they make different choices. But yes, I agree with you that like what the nature of the constraint is a super interesting question. It's just not one to which we feel like we have a good answer at the moment. So the sort of takeaway for us of examples like this is to show that there is a conflict between goals of decision and communication. And consequently, that the recommendations of the classical model, right, that is the recommendations of the sort of usual model we use to think about optimality in sort of statistical settings may not actually achieve the goals of a scientific analyst who cares about communication. Now, fortunately, right, on the one hand, this sort of says the usual model does not seem to, does not necessarily capture the goals of someone focused on communication. Fortunately, in this example, communication optimal rules seem much more in line with what people do in practice, right? For example, if we just think about this case of audit studies of unemployment, we're not aware of any that report only the sorted data, although many report unsorted results. That said, Croft, Lange, and Noto-Adigdo actually ran an audit study and report both sorted and unsorted versions, right? So they actually did run the experiment, estimate these callback rates, and then apply the sorting procedure to report the sorted curve in addition to the raw data. Right, so in that sense, I would think of this not as a critique of what people are doing in practice in these settings, but more as a way that the optimality criteria we're writing down don't seem to match what people mean to be doing, at least in many of these cases.
That's kind of a funny one in terms of thinking about the nature of the constraints, right? That somehow you can report both, but that's very costly.
Oh yeah, no, again, right, sort of again, right, in this case, I'm not in any way saying, oh, I think that we've got the constraint here. Like there are many cases where you can report both. The point is just that these are different criteria. And so if we knew what the right constraints are.
We're not disagreeing.
Yeah, exactly. All right, so any questions before I move to generalizations and implications? Cool. So, so far I've just showed you an example. In the paper, we think about more general settings. And we provide sufficient conditions for an admissibility conflict of the type I just sketched to arise, right? Basically, the conditions are sort of sufficient conditions such that any good decision rule has to discard useful information, right? If that's true, you get an admissibility conflict. Now, we also provide results for other optimality criteria, right? So far, I just thought about admissibility, right? So basically, one rule being better than the other for every prior. Right? That's sort of a strong sense in which things could be comparable. In the paper, we also talk about weighted average risk over the audience, right? So basically, what if I attach a weight function to different priors and say I'm sort of is A better than B in a weighted average sense? There, we basically show that the negative result extends directly, right? There's actually a close connection between weighted average optimality and admissibility. So sort of those two turn out to be irreconcilable. Interestingly, if I focus on worst case risk, right, so sort of minimax risk over the audience, so thinking about the agent who's worse off, then we actually get a positive result. So basically for minimax risk, if the set of priors in the audience is convex, basically meaning closed under a mixture, right? So sort of if I have someone with belief A and someone with belief B, there's someone who puts weight 50-50 on each of them. Then a rule that is minimax for decision is also minimax for communication. Right, so it turns out that actually, if I'm focused on the worst off agents, I can actually reconcile these two optimality criteria of sort of optimal decision and optimal communication for the same audience. Oh, and I guess, yeah, one thing to flag, one thing that is a little interesting on that is it's minimax optimal with no constraint on the communication space, actually. Right, so sort of, it turns out that for the worst off agent in the audience in terms of their prior, reporting the minimax decision rule is as good for that agent as reporting the full data. Right, so sort of that is a case in which summarizing by the minimax decision rule is actually without loss, without a constraint on communication. So actually near the end, so let me turn to implications for practice. So as Max and I were talking about earlier, right, one thing that's going on in this example is that an analyst who's concerned with communication can solve the problem by just reporting the full data X. Right? In some sense, like I have a simple solution, I could just report the full data set. That said, right, as a description of sort of how should we solve the optimal communication problem in scientific practice, that feels kind of unsatisfying. Right? In particular, if it were enough for us to just report the full data, right, no one should ever write a paper using publicly available data. Right? Because in some sense, all of the statistical results I'm reporting in the paper follow from the data. So why shouldn't I just like post the data on my website and call it a day? Right? Coming back to Yang's question, you could imagine a case where like my prior is adding information, but then I should just report the data and my prior and call it a day. And so the fact that we don't do that, right, at least I feel like I learn things from reading papers written with publicly available data, suggests that there's some sort of communication or information processing constraint, right, that's going on in the background.
Just
Yep.
I used to very much think that it has to be that.
Mm-hmm.
I feel now that it could be either that or agency issues that kind of have similar implications.
So yeah, could you say, well, what sort of agency issue?
So imagine I don't know what you know, and you can selectively tell me what you know.
Mm-hmm.
Then that will lead to similar kind of selective reporting or like partial reporting.
Yeah, I mean, in some sense, in that, right? Okay, so that's fair. So in that case, right, I guess I would say you could think
I
of.
really think this is
Yeah.
super interesting, relevant in practice.
Yeah.
I just think like formally, it's not the only thing that can be true.
Yeah, I mean, in some sense, right? I guess I would. So agency issues seem totally plausible to me as an explanation. I guess so there's two things I would say. I guess number one, the fact that I guess I would say the fact that I feel like I learn useful things from. I sometimes feel like I learn useful things from going to seminars where people present results based on the ACS. It feels to me like I personally have failed to fully ingest all the information about the ACS. Now, the second point, right, I do think, right, I think maybe another way to think about this is as what's the nature of the communication constraint, right? And so with agency issues, right, there may be a limit on the information I can credibly communicate to you, right, or on the information that I'm going to communicate to you in equilibrium, right? And so I think that totally makes sense, right? It's basically like agency issues acting as a limitation on what I can credibly communicate or sort of what I'm going to communicate to you.
And what you're going,
Yeah,
right?
exactly.
So I mean, you have like X1 and X2, but you only report X1, but
Yep.
it could be because I don't know that you have X2 or
Yep.
because it's too costly to report
Yeah.
X2.
Oh yeah, no, totally. And basically, I guess what I would say is I totally agree that I think there are settings where agency issues feel like a good description of some of the constraints going on. I sort of also do think there are some settings where I don't totally see the agency issue.
Yeah, absolutely.
Right.
I think pre-registration kind of very much ties into these agency issues. Right?
Yeah, no, exactly. Yeah, no, I totally agree with that. But yeah, sort of regardless, it seems like there are some reasons why we communicate in the ways we do, and there's some sort of limitations on our ability and or our willingness to fully communicate sort of everything we know, everything we observe, everything that's in the data, everything that's in our prior. Now, if we take those constraints seriously, we can think about the question of optimal constrained communication, right? If I could sort of write down what the constraint is, I could think about what's the optimal communication rule subject to the constraint, right? Similarly, if I had the right model for agency issues, right, I could ask sort of, what's the most communicative thing I could get the analyst to report subject to the agency conflict between the analyst and the audience? Now, in all of those cases, the form of those optimal rules are going to depend on the details of how we model those communication constraints, right? If I'm sort of getting something that's constrained optimal, I sort of have to know what the constraints are. So for that reason, today, I have nothing to say about optimal rules, about optimal communication rules, because I don't have a good model for the constraints, other than this result that basically minimax decision rules are minimax communication. So if you're happy with minimax, we have a positive result. Less ambitiously, right, sort of stopping short of trying to think about optimal rules, could we think about just some simple practical ways for an analyst to reduce communication risk? I've got a couple papers with Jesse as well as with Matt Jenskow thinking about sort of issues related to that, including a paper on transparency and structural research, where we're sort of thinking about cases where people are estimating these complicated, non-transparent models and the things that people can do or maybe should do to try to sort of give the audience more of a sense of sort of what's going on behind the scenes in the model to let people sort of better update their beliefs. Similarly, showing results on sensitivity to misspecification can be interpreted in the same spirit. So that actually wraps up what I wanted to talk about today. So the main point in this talk is just that focusing on communication rather than decision-making can change our understanding of the goals of an empirical scientist. In particular, sort of focusing on communication can lead to very different recommendations for sort of what we should report than the classical decision-theoretic model in some cases. And our hope in working on this project is that the change in perspective may suggest may help suggest good procedures for communicating scientific results. So any other comments, questions?
Could you say a little more about the paper with Jenskow and Shapiro and what kind of practice? I mean, actually, as a person who's trying to write a structural model, I'm like, what should I do? What should I do now?
Yeah, absolutely. So well, I'll start with this one actually, and then go to that one. So this one, the 2017 paper, the basic idea is just so the starting point for that project is that if you just look at people who are estimating structural models, it's very, very, very common that authors make statements of the type, our estimate for the welfare loss from this policy is primarily driven by blah, 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 list of data features. And so there's sort of two questions that immediately suggests. Number one, what do those statements mean, right? And sort of in what sense could that statement be true? And number two, why are people making it, right? Because in particular, if you think about the usual optimality theory, right? If I say my goal is to report something as close as possible to the truth, then it's not actually clear why I care what features of the data are driving my conclusions, right? If basically I tell you I've used an efficient estimator, and that efficient estimator is some very, very non-intuitive transformation of the data, well, if all you care about is something as close to the truth, and you believe me when I tell you that it's efficient, we're done, right? It could be driven by some bizarre data features, but if all I care about is being close, that's fine. On the other hand, if we introduce a model where I don't fully believe your model is right, so I think your model is a little off in this way or that way or that way, then maybe I actually care quite a bit about what exactly in your data is driving the result, right? Because if your estimator is some relatively simple transformation of your data, and I think I have a sense of how your model is wrong, then I actually can figure out how to basically bias correct your estimator to better reflect what I think the true parameter value should be. And so basically, what that shows is that if you have a case where the audience doesn't fully believe the analyst's model, right, basically there can be gains in communication from sort of this sort of thing, basically saying what drives my estimator can improve the communication value of an estimate in that case. And basically we sort of work out formal sensitivity measures that sort of can serve that purpose. In this paper, we sort of take the idea here and some other work we've done and kind of combine it with the communication framework here and sort of work that out. We also basically talk about some other things you might think about doing, right? So for example, one point we make there, a big part of what we're doing there is sort of looking over things that people do in empirical practice and sort of looking at them through the lens of this model, right? So for instance, right, sometimes folks will estimate a structural model and get a conclusion, right? So I find that this policy reduces welfare. But it's not entirely obvious from sitting in the audience whether the model actually could produce a different conclusion, right? Like in some sense, if someone writes down a model such that the market equilibrium is always efficient, and then you sort of have an intervention, well then they're sort of by assumption, right? Like they're sort of assuming that like the thing was efficient before. So depending on their measure for welfare loss, you might have to get a welfare loss. And so in that sense, sort of one type of thing we talk about here is basically showing what would have to be different about the data for your model to conclude something else, right? As an example of like another type of thing that you can do to make your model more transparent, right? Because that sort of builds in could your model have actually produced the other conclusion? Because if your model can only produce one conclusion, and then you tell me that's what it's concluded, I probably shouldn't update my beliefs at all, right? So those are just sort of two examples of the sort of thing we're doing here, but the basic idea is like thinking about these sorts of complicated, non-transparent models through the lens of this type of a communication setup and asking sort of what can be done to make the models more, to sort of make the results of those papers more useful for an audience who doesn't fully believe the model. But yeah, this is sort of a review article, and so if you're sort of interested, I would say this is a good one to look at. Yeah. Other questions? Yeah.
Related to this, on this question of how the data have to look like to get the result that this model predicts, like what's a good way to compare that? Well, how do I compare like a data that would predict this versus the data would predict that? Like, do you have an example of metrics that would be useful to look at?
I think that's a super interesting, yeah, I think that's a super interesting question, right? I mean, basically what we say is just that it would be like, it is helpful to exhibit an example, right? So in some sense, but I think the question of like, what's the best way to do it? I think is a super interesting question, right? Because you could ask, if I estimate the model and get a given conclusion, what's the sort of smallest, right? If I pick a metric on the space of data realizations, what's the smallest change in the data that would be necessary to reverse the conclusion?
Exactly.
Right. There's a little bit of work in recent work in econometrics that sort of has a flavor somewhat like that, but not quite, right? So basically there's a little bit of work in econometrics that basically thinks about, imagine I have a set of model assumptions and I start relaxing the assumptions, right? And it basically asks, what's the smallest relaxation of my model's assumptions such that I overturn a given result, right? But that's a bit different than this, right? But that sort of, it sort of fixes the data, changes assumptions, right? Versus let's fix the assumptions, but change the data, right? So I am certainly not aware of anything in econometrics that sort of does that version of it. I think it could be a very interesting question, but we sort of just say it would be helpful to exhibit a data realization.
And I would think of that as like model robustness versus like adversarial data manipulation.
Yes, exactly.
If I was going to relate it to what we've seen from the computer science side.
Yes, exactly. Right. In some sense, it's like model robustness versus data robustness in some sense, right? Yeah, absolutely. No, I mean, and I think that would be a very interesting question. I mean, I think there's an interesting question of sort of what's the right metric, right? And in some sense, the metric would sort of be about like, if I think of it in an adversarial framework, what levers do I think my adversary can pull to mess with the data?
It seems to connect tightly to kind of classical testing theory, where they do like a KL projection into the subset of measures that gives a different conclusion, right? And then seeing how hard, it's basically like a likelihood ratio test at the end of the day, I guess. If you can do that projection, yeah, exactly. Yeah. No, I agree. I mean, I think, or a wall test or whatever.
Yeah. Right, but in some sense, to connect it to like the adversarial version, in some sense, that feels like the natural thing to do if I'm imagining an adversary who can mess with the distribution of the data in KL, basically, right? Would sort of be when the KL projection feels natural, right?
Yeah, I guess it's like, do you care about adversary versus random noise?
Right, exactly. Yeah, I mean, random.
Bringing us back to.
Yeah, I mean, I would say many of these models are so like, it depends on the model. Some of these start like, I guess, for the case we were thinking about here, right? We were basically starting with we were thinking about these cases where you're not even sure that the model can produce a different conclusion, right? And so for those cases, in some sense, just showing that there exists a data realization that gives you a different conclusion sort of is helpful. But then I agree, you can like sort of you could build out more of a framework than that, right? You could think about sort of writing down a more ambitious, like basically saying, can you give me a different conclusion? Is sort of a very unambitious version of this goal, but one that nonetheless is sometimes failed. So like, it's good to be able to at least do that. But I totally agree that you could think about writing down these sort of more ambitious versions of the problem, and I think that would be super interesting. We do not solve that at all.
This is probably dumbing down the conversation, but I sort of sense a topic of dealing constructively with misspecified models, both as the producer of that model and the leader of that model.
Yes.
And when I was taught econometrics,
Mhm.
I was taught a very strong allergy to misspecification,
Mhm.
really encouraged to hate it and
Mhm.
to strive to completely stamp it out. I was very struck by your earlier talk when actually that itself can introduce a bias in future out of self-use of the model.
Yeah.
Have you observed a change in attitudes towards misspecification? I mean, also driven by the machine learning people's success, because they seem to not really give a damn about misspecification. They've done great things. I wonder, so I guess I'm asking, has this changed?
I think it has changed a bit, right? I mean, I think the sort of, if you go back to like the sort of 70s approach in, econometrics, right? Or sort of, and statistics actually to a substantial extent, right? The view was very much sort of, you fit the correct model to the data. And right, this even went for things like, oh, what about estimation when the data are heteroscedastic? Oh, well, you should model the heteroscedasticity and then fit weighted least squares, right? What about time series? Oh, you should model the time series dependence and then do generalized least squares, right? But, right, I think I start with the standard error point because I think that's one where you can actually see quite a bit how the mindset has changed, right? Sort of these days, the standard practice is you use heteroscedastic robust standard errors, cluster robust standard errors. Almost no one is going to say, oh, the best thing to do if you think your errors are heteroscedastic is to fully model them and run weighted least squares to get the optimal estimator, right? And so in that sense, sort of, I think that's one place where we've seen this move towards sort of more comfort with robustness. Another way to look, right, another example of that I would say is actually in the sort of local average treatment effects paradigm and treatment effect estimation, right? You could basically think of treatment effect heterogeneity as a version of saying the linear regression model that people are running for two states least squares or something is wrong, right? Because treatment has different effects on different people, right? And so in that way, right, when we sort of run this model with a single coefficient, that's wrong. There's a distribution of coefficients. Now, one approach to that would be to say, oh, let me model the distribution of coefficients and sort of go down that route. Instead, where we sort of converged is to basically say, well, like modeling the distribution of coefficients and trying to recover all heterogeneity turns out to run into some like pretty fundamental identification problems. And so what many people at least do is to run relatively simpler models and then think about what is the interpretation of this coefficient that I get out of my simple model when the world is complex. Right. And so in that sense, that is also sort of a version of like, I'm sort of no longer trying to say, I'm going to make the model well specified. I'm instead going to say, I'm going to run this thing and then think about how to interpret it. Right. Now, sort of structural models have not, right, sort of when people are estimating more complicated structural models, the interpretation is more opaque. Right. But in some sense, I would say, my view in that area is somewhat the same, right? Basically, is that many of these models impose many, many, many assumptions. It seems heroic to assume that they are literally true. And in some sense, saying we should not use them if they're misspecified, to me, basically says we should never, ever use them. But then there are some questions, right? Like if I want an estimate of counterfactual welfare in certain contexts, I kind of have to make a bunch of modeling assumptions to get that. And maybe there are reasons why I need that, right? The policy decision is going to be made to say, oh, it's hard to get the right model here. I should just give up. That feels unhelpful. And so instead, I guess I would say the approach I would take here is there are various good reasons why we might need to estimate these complicated models. And so then the question is, given that we need these models and that they're almost certainly wrong, what do we do about that, right? And sort of how best to handle or interpret what we're getting out of these models that we need but don't fully believe.
Yeah, and it seems that bringing the decision to the fore was an important part of that.
Yeah,
reorganizing.
Yes, exactly, right? Because I think then the question is, like, we need them for a purpose, right? And in some sense, the answer of what I should do with what I should do with the numbers coming out of these models almost certainly depends on the purpose I'm trying to use them for. So yeah, in that sense, I guess that is definitely an underlying theme here. Also, I mean, in some sense, even if I sort of for some reason fully believe my model, you almost certainly don't, right? And almost certainly shouldn't. So even if I fully believe it from this communication perspective, it's actually still important to try to do this exercise. Awesome. Any other questions?
Yeah.
Great, thank you very much.